Hey everyone, this is Dr. Walker. In this video, we're going to go over another example of using Gauss's law, and this time it will be a problem with cylindrical symmetry. In this problem, we have a line of infinite length, positive charge, and we have to find the electric field a certain distance away from it. So we know that we can use Gauss's law, and the trick first is to find the appropriate Gaussian surface. Whenever we have a line of charge or a cylinder of charge, that cylindrical symmetry, we're going to use a cylinder for our Gaussian surface. That's the first step. And do we need a finite cylinder or an infinite cylinder? Well, it has to be a finite shape, first of all. So it's going to have a finite length L. And it's okay that the distribution is infinite. You'll see why. So first of all, let's see why this cylindrical shape is good. Well, the field is constant over the surface because we're always the same distance away from that charge distribution. So the field will be constant, and the electric field is parallel to the area element, the surface area element. So it satisfies our conditions. It will simplify Gauss's law. The E is constant, and we just need to integrate over the area. We also need the charge enclosed and divided by epsilon naught. So you may think at this point, well, let's find the surface area of a cylinder. However, we don't need a surface area of the entire cylinder because the flux is only through this curved part. If we look at the flat end here of the cylinder, we know that the field goes radially outward from the line of charge. So the field is parallel to this flat end here. So none of the field is going through this flat end. There's no flux through the ends of the cylinder. We only care about the curved surface. That's the only area that we need. The area of the curved surface is 2 pi RL. So this is why it was okay to have a finite cylinder, because it allows us to not worry about any contributions through the ends of the cylinder. Now, if the line of charge was finite in length, then this would not be possible, because if it was a finite line, then the field would not be going straight outward. There would be some sort of angle, and we could not disregard the ends of the cylinder. Okay, so that being said, the next thing is we need to figure out what is the charge enclosed within our Gaussian surface. We have the definition that the charge density is the charge per length. So that means that the charge enclosed is just going to be the charge density times the length of that surface. So lambda times L, right? We want the charge enclosed within this Gaussian surface. And there we are almost done. Now we can just simplify, cross out the L, and solve for E. We're going to have lambda over 2 pi epsilon naught divided by R. And if we want, we can write this in terms of Coulomb's constant. It's going to give us 2 times Coulomb's constant, lambda over R. And the field will be, once again, in that radial direction. So to summarize, if we have a line of charge or a cylinder of charge, we can use a cylindrical Gaussian surface to simplify Gauss's law and solve for the field outside a distribution. And we can also find a field inside a distribution if we have concentric cylinders. We'll do that in a different example.